Good afternoon, everyone, and welcome to RTDology, Burns Engineering's online training series. I'm Jeff Wiggin, National Sales Manager at Burns Engineering, and presenting today will be Bill Berquist, Principal Application Engineer.
Good afternoon, everybody. So today we're going to talk a little bit about kind of the who, what, why, when, and how of calibration or verification of an RTD. Kind of the takeaways from today, we're just going to learn how to identify the difference between calibration and verification, why you should do it, when, and then some of the equipment that's used for actually doing the either verification or calibration. First off, though, I wanted just to throw out some terminology stuff that we'll be throwing around a little bit. The first four there are probably the most commonly used ones. R0 is just the measured resistance of an RTD at 0 degrees C. It's a very important point for determining the accuracy of an RTD. And insulation resistance, just a characteristic of an RTD that ensures that it remains stable and repeatable. And a dewar is just basically a thermos bottle container that's used for doing an ice point test of an RTD. And then SPRT, if we're doing a comparison calibration, you'd use an SPRT to compare your test units to a known standard that's traceable back to an international standard. And the rest of these here, we'll probably use those once, but there's all the definitions if you care to keep track of that. So I had a call a while back from a company, and they needed a new temperature probe, or they were kind of wondering also why it was giving them some odd readings. I had a few questions about some of the history of the part and what it was measuring and things, and they really didn't know. They had never really tracked that particular part. Someone had just noticed that it wasn't behaving correctly. They weren't really sure how long it had been that way. So, and this is not an unusual situation. I do get this question frequently. And what can happen, this can actually end up being kind of a waste of energy. It may be affecting your product quality. And sometimes I've seen where a bad temperature reading and somebody just turns a dial somewhere to kind of compensate for it a little bit, and that's usually not a real good way of handling the situation, because if that probe has shifted a little bit or done something odd, chances are that is not a repeatable error. So just turning a dial to get some required output generally is not the best way to do it. So there's a couple different ways that we can look at testing an RTD for accuracy. One would be calibration, the other is verification. Calibration is going to include several temperature points so that we actually characterize the resistance output of the RTD over a given temperature range. There's not really any adjustment that we can do to the RTD. This is just checking it at various temperatures. Using that information, we can plug that into a series of equations and define the resistance versus temperature output over that temperature range. On the other hand, a verification is just a test to make sure that the temperature probe still meets the interchangeability requirements of when it was manufactured. A couple of the standards that are used are this ASTM 1137 and the IEC, which is the international standard 60751. They define a range and tolerance band for RTDs. These verification checks, you can usually do those in a lab, or you can do them out in the field. It's generally pretty easy, quick test where we'll maybe just be checking the resistance at 0 degrees C. And why would we want to do this? We touched on it a little bit, but just to ensure that we've got a good, accurate measurement. You may have some third-party or quality system requirements. And for sure, we want to keep track of our product quality, especially if you're, food, beverage, pharmaceutical. Lots of other processes are highly dependent on an accurate temperature measurement, not only for safety within the plant and the products that are being made. Make sure that we have an efficient use of energy. Really bad accuracy can cause a lot of wasted money and wasted product. Just a little example here of, this is just heating water from, typical municipal supply, heating it up to 100 degrees Fahrenheit. And if you're off by just 1 degree Fahrenheit over a year, it's $1,800. And that can add up pretty quickly if you've got several of these processes going. And it's just an example of it really pays to ensure that you have a good, accurate temperature measurement in your process. When a new plant is being commissioned, it's a good idea to go ahead and establish some kind of a baseline of performance for all of the instruments. Specifically, an RTD, we'd want to ensure that nothing happened to that probe while it was being shipped to the site, installed, make sure all the wires were connected up correctly. As for an example, in a case of a 3-wire RTD, you may have a situation where somebody, they maybe put a jumper between 2 of the leads to make it act like a 2-wire probe, and that can cause a rather large error. And I've had that happen before. For whatever reason, they thought putting that jumper between the 2 leads was necessary, but it screws up the lead wire compensation. So anyway, this is just to make sure that we've established a baseline of performance for that temperature point. And then as we do some ongoing calibration or verification, that helps to determine the behavior of that particular probe in that location. And it's not only that, but it also helps keep track of whatever instruments that probe may be connected to. RTDs do drift over time, and by doing some ongoing calibration verification, you're going to be able to determine what that is. And one of the most frequent questions I get about calibration is frequency. How often do I need to do it? And there really is no good answer to that, other than that you need to be comfortable with whatever time frame that you choose. We have some customers that will calibrate a temperature probe before and after a batch process, for example. It might be a real high value product, and they want to make sure that the temperature probe did not shift during that process. So they'll do actually a full calibration before and after. Another version of that, or another variation, would be to just do a verification. You may test the probe just at 0 degrees C before and after a batch process. Some of the other things that would determine a frequency, maybe some third-party requirements, whether it's FDA, USDA, whoever it might be. They may say, well, you got to do it at least, X number of months. So they pick like a calendar time, which, that can be okay. It's probably not my first choice of how you would want to set up that frequency. The manufacturer of your temperature equipment may have a recommendation. They'll look at, you know, if there's any vibration going on in the process, any mechanical shock, temperature cycling, and based on all that, we can grind all that together. And what it really kind of boils down to after all of this is it's just kind of your best guess as to how frequent you're going to need to do this calibration or verification. Some of these factors, again, are with RTDs, and this also holds true for thermocouples too. But for RTDs, they will drift, and the more vibration there is, more mechanical shock, more temperature cycling, or just running at a high temperature can cause them to drift over time. Again, product value, higher value product, you're going to want to increase that frequency so that you just have a good comfort level that that temperature point is still measuring accurately. Have some other processes where actually erosion of the temperature probe or thermal well can be an issue. And those would be, they're not only just testing the temperature probe in that situation, but they're also looking at the thermal well, or if it's a direct immersion probe, to make sure that the sheathing hasn't eroded and started to expose the temperature probe. Same holds for corrosion. And then some processes where you have a product that adheres to any intrusions into a pipeline or a tank where it can build up on it, that can actually slow down the response time of the probe. And it ends up in some situations where if the product temperature is changing rapidly, then the temperature probe can't keep up to it. That's actually a temperature measurement error. The probe may still test okay, but because of this product buildup around it, it's going to slow down the time response, and it's not going to keep up with what is actually happening in that particular process. So when we have a temperature probe running at a high temperature, from this graph we can see that we have quite a large drift rate here after 1,000 hours at 500 C. You know, we're 0.3 degrees C, which is pretty significant. Down here at 300 C and below, you know, it's always 0.0 something over this first 1,000 hours, and that'll tend to flatten out over time, this error source. But initially there is going to be just a little bit of this drift due to running at temperature. Now, if we're cycling temperature back and forth, the repeatability of the probe comes into play as a potential error source here. And that's also going to come into play into how you set your frequency of calibration. We look at, now maybe a realistic number might be like 200 cycles, and this might be over, well, let's say 6 months time. And, you know, we're up here, you know, 0.15 degrees C roughly. Some processes, that might be a big deal. Some, maybe not at all. But it is another variable that comes into play. So just to kind of boil this down here, and some other things that you can do to help determine a good frequency level. Again, you need to set this to your confidence level. We could take several different temperature points that, you know, maybe they're all measuring, you know, a fluid temperature at various points within the facility. We can group all that data together and see what's happening over time. So we may just take do a verification of the probe at 0 degrees C and just track that over time on all these different locations and see if there's any drift similarities between them, and it gives you a little better data set as to how to make a good decision on calibration frequency. Again, manufacturers can generally make some pretty good recommendations of, you know, it might be most likely a rather conservative number as to calibration frequency based off of the process characteristics. And then there's always the third-party requirement. And with any of these, if you can go through 5 cycles of calibration or verification without a significant shift, then we can go ahead and double that interval. So let's say you start out at 6 months, you don't see a problem. You can go ahead and double that interval after you've gone through at least 5 cycles. And with that, I think, Jeff, I don't know if we have any questions yet.
Yeah, just a reminder to everyone that we've got a lot of information that's being presented. So if you do have a question, something you don't understand, or you need some clarification, go ahead and type it into the chat box or the Q&A section on your screen, and we can go ahead and get those answered just as quickly as we can during the session. We usually just have you type them in rather than opening up the phone lines, because we've got you know, quite a few people on, and we have a lot of feedback issues and whatnot. So just go ahead and type it in, and we'll get an answer to your question.
All right, good. Looks like the next section here, we're just going to look at some of the equipment that we can use to do the calibration or verification, and the temperature scales, and there I mentioned some equations earlier that get used to define the resistance versus temperature. Then some methods of calibration verification, and then there's some additional options that we can talk about too with full calibration. So first off, again, the verification will just be comparing or testing the temperature probe to make sure that it still meets the initial numbers that are defined by the 2 standards. And then if we were to do a full calibration at several points, that's a characterization. So that actually tells us exactly what that temperature probe is doing over a given temperature range. And one of the first things that we want to do when we're doing either calibration or a verification is to check the insulation resistance of the probe. This is important because if there's any moisture that got in the probe or any other contaminants and it has decreased this insulation resistance, we can end up with a temperature measurement error, and that error is most likely not repeatable. Pretty easy check to do. We just get a meg ohm meter, bundle the leads together, touch it with one probe and the other one to the probe sheath. And that just measures how well the insulation inside the probe is protecting the little platinum resistor that's in there from any kind of moisture. If we get any moisture inside, and this type of sensor here where it has these little coils of platinum wire, if any moisture gets in here or back in this area where the leads exit, it actually bypasses the platinum, and it's just kind of using that moisture as the path of least resistance, and that's where electricity is always going to go. It's just that path of least resistance. And we can end up kind of bypassing some of those little coils, and you get a low resistance, which means a lower measured temperature. At room temperature, you should see about 100 megohms. A lot of manufacturers will test up to 500 megohms, and they may even use a higher voltage. The reason for that is that as the temperature increases, the ability of the insulating materials to do their job decreases. And also, it's probably a higher quality check. So if the probe is even drier or less contaminants inside, more, higher purity materials are used, you're going to be able to get a higher insulation resistance number. And so that's really important at the higher temperatures. At room temperature like this, if you were going to only use a probe at, let's say, 20 degrees C, 70 degrees Fahrenheit, an insulation resistance of maybe 1 megohm is probably all you really need to get a fairly accurate, repeatable measurement. We can look at a little example here of how this is calculated, and I'm not going to go through all the math, but just to get down here to an insulation resistance of 0.1 megohm, we're going to have about a 0.26 degrees C lower reading than what the actual temperature is. So it's, the actual error is not that large, but it's a repeatability issue, and you'll just have some potentially erratic measurement readings. So IR, the very first thing you need to do when you're either going to calibrate the probe or do a verification. One of the first temperature points to check would be in an ice bath, and this is typically done with a verification check or a calibration. We'll put the probe in the ice bath, measure its resistance at the 0 degrees C, and it's a real simple check to do. Just use crushed ice made with purified water. Could just be distilled water that you freeze up and crush it to they're probably 1/4 inch pieces of ice. Pack it into an insulated container. It can be a fancy dewar like this with all stainless steel and a vacuum insulated, or it can just be a the styrofoam igloo cooler just packed full of crushed ice, and then just pour in enough purified water to kind of fill up the gaps in the ice. You don't want the ice to float. You just kind of want all the air to be displaced out of it. And you can see here in this example, you can't really see the water level here. It's probably 1/4 to 1/2 inch below the top of this ice, and the probes are inserted right up to this little transition piece. Most probes you're going to need about 3 or 4 inches to get a good, accurate characterization of what the resistance is at 0 C. And then the two standards they vary a little bit. The IEC has a little wider tolerance band at higher and lower temperatures as you move away from 0 degrees C. At 0 C, they're going to be the same. For a Class A probe, it's going to be plus or minus 0.06 ohms. So it'll be at 100 plus or minus 0.06 ohms. And for a grade B sensor, it's going to be plus or minus 0.12 ohms. And if you check the probe at temperatures other than 0 degrees C, you can use these equations to determine what the tolerance band is at those temperatures. We just plug in the absolute value of the temperature here, and that'll give you your plus or minus degrees C tolerance for that particular temperature. Now, if we were going to do a full calibration of a probe, we'd get into looking at some of the temperature scales and how they relate resistance versus temperature to a mathematical equation. And this has evolved over the years, started back in 1927, and I think it was probably the National Bureau of Standards is what it was called back then, and it kind of changed its name over the years, and this IPTS was the International Practical Temperature Scale, and then they just changed it to ITS in 1990. back in 1968, we had kind of limited computing capabilities, so the equations were simpler than what they were when it was developed in 1990, when we had the advent of a little more computing power. We could use more complex equations and get a more accurate mathematical simulation or definition of the resistance versus temperature curve. With the platinum sensors, the curve is not completely smooth. There's some little dips and things in it that happen over its full temperature range, and the ITS 90 equations take a lot of that into account. So it's going to be a more accurate calibration when it's done to ITS 90, and the R versus T numbers are defined that way. It's usually reserved for laboratory type sensors. The IPTS68 equations are still accurate enough for most industrial applications. You may have seen this equation. It's a Callender-Van Dusen equation. A lot of times it's abbreviated, just CVD. You may see CVD coefficients listed in a, like if you're trying to match the temperature probe to a transmitter, for example, it'll ask for those coefficients in the transmitter software. The other difference between these two, ITS 90 will use a triple point of water resistance, which, going back to our definitions there, triple point of water is where it's 0.01 C, where water can exist at a vapor, liquid, and a solid all at the same temperature. And it's fairly unique material that way. And it's one of a, it's defined as a fixed point because it's always that temperature no matter what. So just like other fixed points. So the Callender-Van Dusen equation, and I throw this up here just to show you that it's fairly simple. You can sit down with a little desktop calculator and punch the numbers into this and do it. With the ITS 90, it gets into some fifth order or something polynomials, and they all have to be solved all kind of at the same time, and uses different algorithms to be able to do that. So, and you really need a computing power to be able to do that. Pretty difficult to do it on a little handheld computer. So now we talked about just doing this ice point check for a verification. When we get into a calibration, we can either do it as a fixed point or a comparison. Comparisons can be done in the laboratory or it can be done in the field. Fixed point, you're pretty much limited to doing it in a lab. It takes a long time. It can be very expensive, and the fixed points need to be treated quite gingerly. So usually doing that in the field is not possible. So the comparison calibration is probably the most common. And so we'll take a known sensor, usually it's called SPRT, which is a standard platinum resistance thermometer, and we'll use that to compare to our test sensors. It can be a real simple setup with just a meter, your SPRT, and some kind of recording equipment to gather the data. Could be a piece of paper, could be a computer, any number of things. And each one of these components that you add into this system adds to your uncertainty level of that measurement. So sometimes keeping it very simple can actually end up with a lower uncertainty level than having a whole bunch of complicated equipment hooked up to be able to do it. But in general, in a lab, you're going to have probably more accurate equipment than you will in the field. And when you're doing these, either the verification or a full calibration, by definition, you should have, and the standards require that whatever you're comparing your sensor to should have an accuracy of at least 4 times greater than the unit you're trying to evaluate. A lot of labs will go 10 times. I know we do at least 10 times in our lab here. So accuracies that can be obtained in a lab range from about 0.001 C to maybe 0.01, and in the field 0.5 to 0.5 degrees C. This will typically have some kind of an industrial secondary standard, so it's going to be a little more durable than like a laboratory standard would be, so it can be used in the field. And if you happen to set it on a table and a little too hard, or if it gets banged around a little bit, it's generally not going to shift on you, whereas an SPRT that you might use in a laboratory, those have to be treated very carefully. You can't even set those on a table, whereas if you put it on a table and if you hear it go click or anything, there's a chance that you might have caused it to shift a little bit. So they can be very fragile and need to be treated quite carefully. Typical lab setup. Here we show this is a low temperature bath that might be set at -80 or -38 C or whatever. This is an SPRT right here that's monitoring the temperature of that bath. We have some multiple input data acquisition system here, and a thermometry bridge that's kind of hidden behind all the cables. And this would all lead back into, it might be a PC that has the data acquisition software on it. Some of the other equipment, this is a liquid bath that uses silicone oil. And if you look real careful, you can see a little copper stabilization block in it that helps to minimize any transient temperatures that may be happening within the bath as it's being stirred and that fluid is moving around. Ice bath we talked about, liquid nitrogen source. It's another very commonly used fixed point. This is a salt bath, which doesn't really show a whole lot because it's a liquid salt and it tends to splatter a lot, so it kind of has to be kept under wraps. Typical thermometer readout, and a lot of laboratories need to track humidity and temperature in the lab, and that's this meter here would be doing that, and then humidity and temperature can affect the accuracy of some of the higher end calibration equipment. So that needs to be tracked and recorded, and if it's an accredited lab, that information is looked at and evaluated during an audit, for example. SPRT like this one is very fragile and can run $10,000, about $5,000 for the probe and another $5,000 for a calibration. Calibration of these is typically done with fixed points, so you might have melting or freezing points of various metals that are used as fixed points. And those are usually only done with a high-end SPRT like this one. These do have a fairly wide temperature range that they can be used over. Again, accuracy is exceptional, drift rates are very low, but they really need to be treated extremely carefully. Fluid baths typically range from -80 up to 500 C. There may be another, like a fluidized bed type thing, which might use some sort of a solid media, and it's fluidized with air. You know, they can maybe go to higher temperatures, but for most RTDs, they're only, you know, they're limited to about -196 up to 500 C. So usually the fluid baths, and in particular silicone, oil, and salt, those are probably the two most common liquids that are used. Water should really only be used in an ice bath. Trying to use it at other temperatures, you know, like if you're trying to hit it at a boiling point, that's dependent on your elevation above sea level. You know, if you're at sea level, yeah, it might be an okay way to do it, but really prefer oil or a salt bath, and then done by comparison. A hot block, it's got a little aluminum insert with the holes drilled in it, and you can vary the temperature on this to, you know, quite a wide range. Accuracy, you can depend on the sensor that's built into this, and you'll have a display here with typically just 1 decimal point of resolution, or you can actually take a standard SPRT, pop it in one of these holes, and do a comparison calibration and get a little more accurate measurement that way. Typical readout device. This one is connected to an industrial secondary standard. And this would just read out. This one's got like looks like about a 3 decimal place resolution. And if you want to get away from the do-it-yourself calibration, there are labs that will do this. Some of the other options that can be done in this situation would be a matched calibration, where you run the RTD through a full calibration over the usage temperature, calculate the calibration coefficients. That information can be entered into the software of a transmitter or some other temperature readout, and it eliminates most of that interchangeability number that we looked at earlier, because it has characterized the actual output of the sensor. So you get a much more accurate temperature measurement for that temperature measurement loop. Some of the equipment that's used there would be, if it's a programmable transmitter, you might use a HART communicator or a software package on a PC. If it's an older analog thing, you can hook up an ammeter and use a decade box to input the resistances that were obtained for that calibration, and do it that way. So it's a little more of a manual type setup. And then outside calibration services, always a good idea to look for an accredited lab. A2LA and NavLab are two that are probably the most common. There are others out there. So you get this defined QA program. You know that the people doing the calibration were trained, and that everything is fully documented, and a very methodical procedure on how these calibrations are done has been followed. They typically need to retain records for a long period of time. Other labs may have special scheduling where you could send in a probe at a given time, and then it can get calibrated and returned back to you in a short amount of time. It also, an accredited lab shows that they have some experience with doing this, and they've gone through a very stringent set of evaluations to be able to say that they are accredited. So with that, Jeff, I don't know if there's anything else that we need to cover with that. If there's any other questions, I was just going to maybe go through a quick summary here.
Yeah, so again, just a reminder, if you do have a question, now would be a great time to type it into the Q&A box or the chat box, and we've got a few minutes left so we can get those answered. Or if you have a question that you want to direct to us directly, give us a call. We'll have some contact information here, and you can feel free to give us a call if you don't want to type it in at this time. So why don't you finish up, Bill, and then we can go through. We've got one question, and maybe some more will come up.
Yeah. So I just wanted to have everybody take away from today would be know the difference between a verification and a calibration. Usually a verification is just checking the ice point just to see that that temperature probe meets that original ice point resistance or within that tolerance band. Again, the two standards define a grade A or Class A sensor as plus or minus 0.06 ohms at 0 degrees C. And if it's a class or grade B, it's 0.12 ohms at 0 degrees C. If we need a more exacting check of the probe, we can do a full calibration where we'll do multiple points. And then some mathematical equations can be used to define the exact shape of that temperature curve. With a full calibration, you can usually get resistance versus temperature table printed out, and it might be in 1 degree C increments or 1 degree Fahrenheit, or even fractions of a degree. If you want to really see a kind of a visual characterization of what that temperature probe is doing. And then one of the most common questions I get about calibration or verification is, how often do I need to do it? And you can look at several factors and lean on the manufacturer of the probe a little bit. They're going to have some, hopefully have some information about how their probe behaves when it's exposed to any kind of vibration or shock temperature cycling. And then another good factor to help determine frequency would be the product value. So if you have a batch process with a high value product, you might want to do at a minimum a verification before and after. And if you really want to know what's going on, do a full calibration before and after. One thing I did not mention earlier is that when you do a calibration, there's really no need to do it over the full temperature range capability of that probe. You should keep that range as small as possible to cover just what that probe is being asked to do. So if you're measuring 100 degrees C, don't do minus 196 to 500 C. That puts the probe through a lot more stress and strain, and you're going to get some wider tolerance band numbers for that kind of a calibration. So you might want to just do 0, 50, and 100 degrees C. And then finally, safety. Within the factory, steam lines and things that can, blow up or cause issues. Just a safety concern for the people that are working there. So anyways, that's about it for today, and I guess whatever questions we have, we can get to those now. Yeah.
So a couple questions. One is for verification. Is it necessary to check another temperature apart from the 0 C or the 0.01 degrees C in order to check the value, or is 1 point sufficient, or do we need more?
Yeah, it all depends on kind of, again, your confidence level in that, or your comfort level with that temperature measurement point. if the probe is measuring okay at 0 degrees C, if it's still within that grade A or grade B tolerance band, chances are it's going to be fine at the either higher or lower temperatures. It's very rare that it's going to be off at other temperatures. But if it's, you know, and again, it gets back to that confidence level issue where, you know, if this is, you know, if you're manufacturing a drug that's real critical that it be processed or stored at a particular temperature, you know, over a period of time, you know, you might not feel comfortable with just doing that ice point check. You may want to check it at, you know, 121 C, for example, a real critical temperature for the pharmaceutical industry. You know, and that give you an idea of if it repeats not only at 0 but also up at the higher temperature.
Okay, and then you had mentioned some checks that should be done with existing sensors. If you purchase a new sensor, are there any checks that should be done on that new incoming sensor, or is that not necessary?
Well, it's good to establish a baseline performance for that particular temperature sensor. Things can happen during shipping and installation, and pharmaceutical applications, you know, they'll go through some process verification, validation procedure where it's very systematic, that they check everything to make sure that it's performing like it should. And I think it's probably important too for a lot of other applications, just from a sheer money standpoint, because you don't want to be wasting energy, you know, either putting more energy into that heating or cooling process than what you have to. And also farther down the line when, you know, you might be cooking some food product and it has to cook for X number of minutes at such a temperature. You know, and if you have a temperature point that's not measuring correctly and you just, you know, turn a dial to turn the temperature up a little bit so you get some kind of an output that you like, that's really probably not the best way to handle that. So doing that initial verification check just to ensure that things were installed and they're working correctly can go a long ways towards making that process run a lot more smoothly and ending up with a good quality product in the end.
Okay, great. One additional question here. Are some RTD constructions more physically robust than others? What RTD should be used in industrial plants where some vibration is likely?
You know, there are some, I guess, you know, when we look at the durability of RTD probes, there are coil sensing elements, and then there are thin films, and some manufacturers will, you know, kind of differentiate between those two. And if the thin films are packaged correctly, they can be very durable. The coil style elements, and that was an example of the one that we looked at earlier with the insulation resistance check. Those coils can only be supported a certain amount, and if you try to support those anymore, they tend to induce a lot of strain, and then your resistance number is going to be very erratic and not repeatable. With the thin films, because of the way they're constructed, they can be packaged in a manner that they can be very durable. So there is a difference there, and you know, whatever manufacturer you use, they should be able to tell you, give you some idea of what the difference is between their particular constructions.
Okay. Well, it doesn't look like we have any additional questions at this time, but if you do have some, the contact information was up a little earlier. Feel free to go ahead and give us a call or send us an email. We do want to thank you for attending, and we look forward to seeing you at future events. In fact, there will be a calendar out here within the next couple of weeks as to what's going on for the remainder of this year and into next year. So with that, also a reminder that we will be sending out a link to this recording. In the meantime, as soon as the recording's available, if you search RTDology on YouTube, you'll find it out there as well. So with that, I want to thank you again for attending, and have a great afternoon. Okay.